domain responses. Not all the things, only we took an example of a step input, and that gave some insight into the performance of the system. Note it carefully that this time response, once it is in a steady state, does not give any other information. That it is in state, that's all it gives. It is in steady state. So what time response gives us is a transience. That is from the way from the time we switch on the input till the output settles to a finite level, or does not settle also. If it's unstable, it won't settle. But generally, we have assumed that we are studying systems which are going to settle down, that is, stable systems. Before I go to the next topic, I would like you to attend to this small screen. On a very simple algebra, perhaps you might have studied much more than this in your lower classes. But I want to stress this point over here because it is this point where many students tumble down. Suppose you are given roots and we are analyzing a second order system. Same thing you can extend for higher order also. Now stop for the time worrying about the order, transfer function or anything. I have a polynomial of second order, say x square something into x plus some other constant, x square plus alpha x plus beta. Suppose you are given the roots of this polynomial. How will you construct the polynomial fast? See, we are in a very, very advanced stage. We are not in 8th standard or 9th standard. We are now much more in that one. So when you teach this to students, they should practice this kind of building the polynomial, because this is essential in analyzing what is coming next. Suppose the roots are -4 and 8. I've chosen one negative and other is positive. It could be both negative, both positive, like that. So -4 and the values are relative, but they don't have any influence on the method. So -4 and 8. So normal way of constructing a dx, that is a polynomial in x, whose roots are -4 and 8 is x minus -4, that becomes x plus 4. X minus plus 8, that becomes x minus 8. That is x minus the root. Root is -4, x minus -4 is x plus 4. X minus 8. Here also I have seen students and some textbooks miss this point. They have put x minus 4 and x plus 8. I mean, by mistake, I don't know how it is. You can find the roots. This is one way of doing that. Suppose it's a complex root. -3 plus minus j5. So instead of -4 and 8, you have got -3 plus j5 and -3 minus j5. Where if you put x plus etc., it is tedious. It is not wrong, it is perfect. But here is a place which we come across many times to construct a polynomial. So I say this method, follow it carefully. I want you to give this method to students. You may also know it. Always principally the root is anything, minus of that is used in our operation. -3 plus minus j5. So just write the polynomial as x minus at -3, the real part. This is x plus 3. X minus -3 is x plus 3. Square it. Plus the square of the j term. That's all. There is no minus here. Look at this one. This is plus j and minus j. Don't put j5 here. You write only, you have only this, you have to use only 5, not j. This point is only equal to 5. and not J5. Clear? So this x plus 3 whole square, straight away x square plus 6x plus 3 square and 5 square makes 9 plus 25 makes 34. This is faster way of doing. I've seen books writing down x plus 3 plus j5 into x plus 3 minus j5. It is correct, but it's lengthy. It will take time. We are not testing the student for whether he can make a polynomial. We are using the polynomial for some other thing. So let us not waste his time or the student's time in trying out this algebraic manipulation. So you please trust his point, x minus the real part. So that becomes x plus 3, its square, and just the real part of j5, that is only 5, not even minus 5 or plus 5, just 5. And if you try the other way, this also is equally coming out. It is, look at this please. It is x square plus twice the negative of the real part is twice, this is coming on the 2ab term, twice of this is the negative of the minus 3. That becomes plus 3. And squaring 3 square and 5 square. So that's one way of remembering it. So twice the negative of the real part into x plus square of the real part and the imaginary part. Sum it up. What are the converse? You may think that I am taking you to the 9th standard or 10th standard, but it's important in the sense that you have to tell this to students. Suppose the other way we want to find the roots. There are ways of many other ways of doing that. Many ways of doing that. So let us take another example. Now it is a reverse process. Qx is given. We are trying to find its roots. First thing is Qx is given. So you go to the first degree part, that is 14x. That 14 you take, and negative of that 14 you take, and half of it you take. So negative of 14, half of it is minus 7. That's why I put it in red here. Take this as a number. Now, this minus 7 is important for us. So the roots are simply this minus 7 plus minus its square. Minus 7 or plus 7 makes no difference in the squaring. Minus, this always minus. Always this is minus. And you have got this 65 is coming from here. This 65 is coming over here. So this is 49 minus 65. It's negative number. So we put j here. So this is 49 and you have got 65. 49 minus 65 becomes minus 16. So j root minus 6, j root 16 minus 7 plus minus j4. This is the point I want to give you. Now let us go straight away into what is in store for us. Let us see the next topic of interest, which is continuing. Can you hear me?
Yes, sir. Okay. Yes, sir. Please continue.
And let me push this up. This is giving me trouble. Okay, now we will go. Why this? I've taken some time, but it's worth doing that. We defined the frequency response of only stable system. What is the frequency response? I have not told you, but this is a point of lot of arguments, etc. This is only for a stable system we can define the frequency response. That is, this, as I said at the beginning, is a steady state response. Time response we get a lot of information on the transients, and this frequency response give more on the steady state performance. We are studying LTI system, linear time invariant system, linear systems. As I stressed yesterday, linear time invariant means time invariant and it is lumped parameters. Parameters are lumped at one point. This is a very, very effective way of you are defining a linear system, most effective way. If you give a sinusoidal input, then of certain frequency, then the response, or what you call as output, will also be a sinusoid of the same frequency, that you have to underline. The same frequency should be underlined. So if you give a frequency omega 1 sine omega 1 t, the response will also be sine omega 1 t. Then what's the difference? Its amplitude may change, and also the phase may change. So in general, I can say that if you give 1 sine omega t or a sine omega t, the response is a into something sine omega t plus an angle phi. This angle is expressed usually in degrees. So frequency response is the response of this amplitude and the phase of the response, this output phase, to sinusoids of different frequencies. So if I apply a sinusoid of frequency omega 1, I'll get a response of omega 1, sinusoid of omega 1. If I have a sinusoid of omega 2 as input, response will be sinusoid of omega 2, and so on and so forth. So for every omega, you have an amplitude and a phase. So the frequency response characterizes an amplitude and a phase of a system. For unstable system, there cannot be any steady state sinusoid output. This is a point which you should stress. The transfer function is Gs, then replace S by J omega. This transfer function is of a stable system. Replace or set S to J omega. We obtain what is called a frequency transfer function. It is a transfer function is domain, S domain. Now you have to convert that into frequency. If you are going to apply a sinusoid of omega, then the output will also be sinusoid of say omega. So transfer function has to be defined, or it has to be transferred into a G of S by G of J omega. The study includes understanding the phase margin, gain margin, and system stability in the run. Okay. What's the frequency response? As told you, express a frequency transfer function in the polar form. So any, for example, is a complex number. Any complex number you can express as a plus jb, a real part plus j times imaginary part. Stress here, the imaginary part is not really imaginary, it's also real, but j times real becomes imaginary. And this can be expressed in the polar form as a magnitude and a phase. So root of a square plus b square will be the magnitude. Tan inverse b by a will be the angle, phase angle. So we call m omega and phi omega. I repeat, gj omega will be expressed in terms of a plus jb, some real part plus j times imaginary part. A will be a function of omega, b also will be a function of omega. So magnitude is a square plus b square, it's a root. And phase angle is tan inverse of b by a, the imaginary part by the real part. This m is called amplitude and phi is called phase. So if I plot against omega, m, so that is the amplitude plot. If I plot phi in degrees, not in radians, phi in degrees against omega in a rectangular plot, that becomes a phase plot. I've shown here this picture I will reuse for some other problem little later on. Here the x-axis or the horizontal axis is, I don't want to confuse the word, the abscissa and the ordinate. Is ordinate and other is abscissa. I want to say a conventional form of knowing the axis as x-axis and y-axis, or a horizontal axis and the vertical axis. That's easy to understand rather than the word abscissa and ordinate. Even at this stage, I confuse what is abscissa and what is ordinate. But anyway, I have given here abscissa as omega and ordinate as the magnitude. Abscissa is the absolute scale. Now, the x-axis here, it is not the linear x-axis. Reason I tell you. This omega varies from 0 to very large number. I don't want to call this as infinity, but mathematicians would love to use the word infinity here. So this omega varies from 0 to much large, 10 to the power of 5, 10 to the power of 6. So if you want to draw on a linear scale, it may be a roll of a paper rolling on the floor for about a mile or so. And that will be your x-axis. Y-axis may be short. So you have to roll your paper on the road and then measure the frequency and magnitude. Oh, that is not convenient. So we use a scale. It is not logarithm of omega. It's a logarithmic scale. The scale is logarithmically distributed. I'm not taking logarithm of omega. Though we say log omega, it is not really log omega which you plot on the x-axis. It is just omega value itself. That corresponds to the value of omega in a logarithmic scale. See, for example, normal scale, say 1 inch equal to 100 cycles per second. So it is not 1 inch here. One segment is 1, second segment is 2, third segment is 3 in logarithmic scale. So when you use this logarithmic scale, it is known as a semi-log sheet. Along the y-axis, the divisions are equal. You can see that the divisions are equal. The parallel lines, horizontal lines are equally spaced. Whereas the x-axis is not uniformly distributed. You see that there is a wide, the width was more on the beginning stage. As it increases, it is thinning down up to 10. The 0 first is, I'm sorry, this is not 0. The lowest, there is no 0 point here. There cannot be a 0 point because minus infinity, log of minus infinity is going to be 0. So we don't have that point here. So we call it 0 in a wrong way, a lowest point. And the first division is 10. So if you can look into that carefully, first division is 1, second division is 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10. The first block is 10. Second is starting at 10, then it is not 11. It is in multiples of 10. Remember this. Never call it 11. 10, 20, 30, 40, 50, up to 10 to up to 100. 10 power of 0 is 1. 10 power of 1 is 10. So this is going to be 10. So this is going to be 0.1, 0.2, like that, 0.8, 0.9, and 1. These 2, 3, 4, 5 to 10, 10 power of 1. The next is not 11. It is 20, 30, 40, 50, up to 100. Then 100, 200, 300, 400, 1,000, 1,000, 2,000, 3,000, etc. This is how it goes. So it is not 1, 2, 3, 4, 5. It is a very small section is of 10. Remember, the left side is when you purchase this sheet. Many boys, I have seen in some of the. I was once an examiner in an electronic circuit lab. One lab, and students are plotted the other way. In your what I mean is, they have topsy-turvied the sheet. The left side was thinner, and right side is thicker. And the argument which they got was, when you see a moving iron meter, the starting point is crowded, farther off point is wider. So they thought it is similar. It is the opposite of that one. That is not logarithmic, that is squared one. This logarithm is reversing of a power. Logarithm is reversing of a power. So I wanted to stress this point. When you take a sheet, this is where x-axis is there, this is y-axis. Now let us go to the plot of this plot. I will reuse for some of the problem little later on. Why do you want this frequency response? That's the point why I want to tell you here. Suppose you have a system to which you give a multiple frequency summed. What I want is it's a periodic wave. So periodic wave is a sum of multiple frequency terms. It could be sine or it could be cosine. I mixed both here. So let us say it is not x of s, this is x of t. This should be x of t. This should be x of t, not x of s. 0.5 minus 0.4 sine omega 1t minus pi by 5. This is input. 0.1 cos omega 2t plus pi by 7. This is input frequency. So input frequency, you have got DC, you have got omega 1, you have got omega 2. And this is the frequency response of a system to which this becomes the input. X is the input to that system. This, to begin with, for various frequencies, I have got the amplitude here, A. For the same omega 1, omega 2, etc., I have got a phase angle. These could be numbers. I've just given a common thing over here so that you can understand how to use it. So the input has three frequencies. One is DC, that is as good as omega 0, and omega 1 and omega 2. Omega 1 maybe will be a number. Remember, it only just omega 1. It could be 0.1 radian per second, 0.10 radian per second. Could be like that. So what is the output? The linear system, if you have split up the inputs, some of the outputs will also be there. Some of the outputs will be the net output. So 0.5 will give me one output. Minus 0.4 sine omega 1t minus pi by 4 will give another sinusoidal output. 0.1 cosine will also give another sinusoidal output. It may be called cosine, cos. So I am splitting this inputs into three sections, 0.5 magnitude, okay, and minus 0.4 with an angle of minus pi by 5, minus 0.4 angle of minus pi by 5, and another omega 2, 0.1 of angle pi by 7. So there are three inputs I've got. So when the input is 1, the outputs are as marked here. So this is what the frequency response tells you. If input is 0.5, so this is 0. Remember, this amplitude will never cross the x-axis. This will be always positive. Again, I have seen a book recently. Somebody gave me a book that contains a negative side here. There cannot be a negative side because amplitude is positive, only a positive value take. So when omega is 0, the output is A0 for input as 1. If input is 0.5, the output will be 0.5 times this A0. That's what the input into the response is. This response is frequency response. 0.5 into A0. So the output will be having one term 0.5 times A0. Second, at omega 1, look at this is sinusoidal term. I have not changed this minus 0.4 into 180 degree, etc. I'm just keeping as it is. There's no change in that one. So minus 4 angle minus pi by 5. And at omega 1, the response for input 1 is A1. And the corresponding phase angle is phi 1. So we have the output as 0.4 minus pi by 5 into A1 angle phi 1. So which is 0.4 minus 0.4 into A1 into angle minus pi by 5, same pi by 5, plus this angle phi 1. Since this is a sinusoidal term, I write a sinusoidal as output itself. So minus 0.4 A1 sine omega 1t and angle is minus pi by 5 plus phi 1. Remember, be careful, pi by 5 is in radian phi 1 is in degrees. So when you add up, this pi by 5 has to be converted into degrees. Make a note there if you want. Another one is omega 2. It's a cosine term I have used. I could have used sine term also, but I just want you to stress this point. Even if it is cosine, you can compute. So the input is 0.1 and angle is pi by 7. So this 0.1 cos. You may make a note here, this cos, this sine, this DC like that. You can make. And the output in the response is 0.1 at omega 2. At omega 2, the response is A2. So we have got 0.1 A2 and the angle for omega 2 is phi 2. So 0.1 A2 and this angle will from the input side, phi 2 is from the response. So we have got 0.1 A2 cos, phi cos because input is taken as cos. Here input was taken as sine, you took as sine. 0.1 A2 cos omega 2t plus angle pi by 7 plus phi 2. Remember again, this pi by 7 is in radian, whereas phi 2 is in degrees. So net output will be this term plus this term plus this term plus this term plus this term. That is 0.5 A0 minus 0.4 A1 sin omega 1, etc. plus 0.1 A2 cos omega t plus etc. So that is how we predict the output from your frequency response where you have the periodic inputs of various different frequencies. So I need not tell that if there is any periodic wave, a sawtooth wave or a square wave, split that into Fourier series, and this will be the terms corresponding to the sawtooth wave or any other periodic wave. So you can determine the output if you know the frequency response. If you have an input as a triangular wave or a pulse or a periodic square wave, you can compute the output using the Fourier series of the input sequence. That is an important thing. And that is why we have shown interest in the frequency response. So I'll go a little faster on this issue. So first we had to draw some response characteristics. There are two response types I've shown in the beginning. That is called a Bode plot, another is the polar plot. We will first of all concentrate upon Bode plot, how to plot it, and then go to the polar plot and therefore use of the polar plot on stability criteria. We have any transfer function will have four types of terms. Any transfer function will have four types of terms. A constant term, K. Poles are zero at the origin. That is a S term in the numerator, pole at origin. S term in the denominator, a pole at the origin. Zero at origin is a numerator, pole at origin is a denominator. I put S plus or minus P. It could be two poles or two zeros, or three poles or three zeros like that. So the P will be 1, 2, 3 like that, number of zeros or number of poles. The numerator term, it is for a zero. Denominator, it is meant for the pole. So 1 by S square means there are two poles at the origin. S cube by something means three zeros at the origin. So this one type of term is constant term. Second type of term is something like S square or 1 by S square like that. So 1 by S is pure integration. S is a differentiation. It's also another way of terminology used. And the other third type of term is a first order term. 1 plus S by something. Or it could be even S plus 3, S plus 7, S plus 9. You can convert that into taking out a constant term. So this is the usual form which is convenient for us to use in the Bode plot. That's why we are given like this. Otherwise, this will be S plus 2, S plus 7, S plus 18, something like that. Take 18 outside, so this becomes 1 plus S by 18. So 18 corresponds to omega naught. It should be either a numerator or a denominator. So a term, first order term, in the numerator is 1 plus S by omega naught. In the denominator is 1 by S plus S by omega. And there won't be both will not be omega naught. One may be omega 1, other may be omega 2. And the fourth one is a second order quadratic term whose roots are complex. If they are not complex, I can split that into the first order terms, product of first order terms. So s square plus 2 zeta omega n plus omega n square, what we have seen yesterday, the same term, but I have removed that omega n square to make it this form, s by omega n square whole square, 2 zeta s by omega n plus 1, power 1 for numerator, power minus 1 for the denominator. And this may various terms based upon zeta and omega. Omega n is natural frequency of system. So an example I have given is, if this is the given transfer function, 20 s plus 2 by s square, s plus 4 into s square, 6s plus 25. If you want to convert into this terminologies, remove 2 outside. So 1 plus s by 2, that's what it is, s square. Remove 4 outside, 1 plus s by 4. Remove 25 outside, and that becomes s by 5 whole square plus 6 by 25, or 0.6 by and is 1. And collect all these constant terms together to give you 0.4 out of 20. So you can this is a small exercise you can try. So if this is the form, but we are going to use this form. But I stress one point here, except to determine k, the same form can be used also, which we will tell you when you plot. So Bode plot is a logarithmic plot. First thing, it's called asymptotic plot. It assumes a very approximate straight line or a straight line approximated graph, or a straight line for any graph. So we will try, suppose we have a transfer function like this, k is 0.4. The first term here is 1 plus s by 2 as the numerator, and there is a s square in the denominator, 1 plus s by 4 in the denominator, and s square etc. term in the denominator. So this is the first term, these two are the second terms, this is second term, this is third term, and this is fourth term, for the type of term. So we will draw the Bode diagram for each term separately, and I am going to take logarithm of the magnitude, so I can add the logarithm of magnitudes individually. So if m equal to m1 into m2 into m3 into m4, log m will be log m1 plus log m2 plus log m3 plus log m4. This logarithm is called, not direct logarithm. We take 20 log that number. You may know why that decibel, etc. are taken because of the power equations in the electronic circuits. So we take the magnitude not as a number, but in decibel. So if magnitude is 10, we take the 20 log 10 as a magnitude, log 10. Log means to the base 10 again. So here log is not ln, it is not natural logarithm, it is to the base 10. That's why your graph paper also was in tens. So 20 log k, we call k suffix dB, another way of writing down. So whatever be the frequency, Ts replaced by j omega, k is not going to change. So the amplitude plot will be in the omega on x-axis in the logarithmic scale, a constant line, horizontal line, whose value is 20 log k. If k is 10, for example, this 20 log 10, log 10 is 1, so this will be 20 dB. And the phase angle is going to be 0 or 180. Do you know when 180 comes into play? When I have a negative number. K is not positive, it is minus 40, minus 200, minus 57, like that. So the angle is going to be 180 degrees. That's why I put 0 or 180 degrees. The next type of the term which I want to use is 1 plus s by a. Am I rushing out quickly? This you draw I'll come to this, take up this plotting. For all, remember this is a general argument for any linear system, linear term. I will again come back to the next slide, how this is going to be drawn. So 1 plus s by a, if you remember that, we have made 1 plus s by 4, 1 plus s by 2 from the term s plus 2 and s plus 4. So assume starting point as 1 plus s by something. A is something like 2 or 4. This a value, okay, omega equal to a is called a corner frequency. Some terms you used to remember that. S that a, not s, that a, omega equal to a. So in the previous example, there is a corner frequency at 2 and a corner frequency at 4. And there's one more at 5 here for second order term. Okay, for all points to the left of omega equal to a, note it down. For all points left of omega equal to a or less than a straight line of 0 decibel. So along the x-axis, one straight line up to omega equal to a. I will show that shortly. Draw a unit slope. This is one definition. Unit slope. How do you do that unit slope? Omega 1 equal to a, the magnitude is 0. Omega 2, another value of omega, 10 times a, it is 20 dB, a straight line. Omega equal to a, the value is 0 decibel. Omega equal to 10a, it is 20 decibel. Draw a line joining these two. That line has a slope of 20 decibel per decade. Decade means 10 times. 20 decibel is jumping up for a jump of 10 times omega. So this jump we call, for our class only or many other places also they use this terminology. This jump is called a +1 slope. Slope is positive. It is not 45 degrees, don't confuse that. It is +1 slope. If the jump is downside, that is if the term is 1 by something, then the magnitude is negative. Magnitude is minus logarithm of this 1 by a number. Logarithm is log 1 minus log that. So minus log comes. So the jump is -1 slope. This you keep in mind. We'll come to that again. Similarly, for the same term, frequency, for a frequency term, omega less than a by 10, the 10 is always used here. For omega less than a by 10, that is up to a by 10, the phase angle is 0 degrees, not radian, always degrees. For all the values omega greater than 10a, the phase angle is +90 for a numerator term, -90 for a denominator term, flat. And take the line joining these two starting and ending points. That will be the phase plot. Now I'll come to that first time again. I have shown over here. So we have got again s by omega naught. 1 plus s by omega naught. I have a point here omega naught. To the left of this, the magnitude is taken as 0 dB. This is a dB on y-axis dB. And at 10 omega 1, that is 10 omega naught, I go to 20 dB. So this is the point for 20 dB, this time for 0 dB. Draw this a straight line. So this represents 1 plus s by omega naught. Come downside, 1 by 1 plus s omega naught, no change. Up to omega, it is 0 decibel. And beyond omega naught, go up to 10 omega naught, it is -20 decibel because this term is in the denominator. So you take -20 because logarithm of a term of a number, the denominator is minus log of that number. So -20 dB here and draw a line. So this line and this line will be mirror images. Okay. I have drawn a dotted line here. Strictly speaking, if you determine for various values of omega and strictly plot, the dotted line will be the plot of the logarithmic magnitude. So this error at this omega naught is very, very small, 2 decibels or less than that, 2 decibels. So we take that instead of the dotted line is the actual line. We say the frequency response is exactly this thick straight line. Come back to the phase angle. At omega naught or 1 by 10th of omega, here is omega naught to 10 times omega naught for the magnitude. For the phase angle, 1/10 omega naught to 10 times omega. See the difference here. 1/10 omega naught to 10 times omega naught. So go to 1/10, so this is the point omega naught. Go to 1/10 omega naught here. So if this is 10, this is going to be 1. This is 17, is going to be 1.7. And to the left of this 1/10 omega naught, the angle is 0. And at 10 omega naught, look at this, 10 omega naught, the angle is taken as 90 degrees. So a straight line here, it is 0, and a straight line here, it is 90. Join these 2 points. This is the angle at any frequency intermediary between 0.1 omega naught and 10 omega naught. Beyond 10 omega, it is mostly 90. So again, the dotted line is the actual curve. So this dotted line is known as a sigmoidal curve. Something like this, S, sigmoidal, sigmoidal. So again, here also for the denominator term, the angle is going to be negative here. So at 0.1 omega naught, it is 0, left of 0. To the right of 10 times omega naught, it is minus 90. Remember that. And a straight line is joined to show that. And this straight line of the phase angle is said to have a slope of 45 degrees per decade. You can see that. This is for 100, it is 90. So for 10, it is 45 degrees per decade. So this is how it is plotted. If the term is S or 1 by S, what's the difference? If its term is S, you take the point omega equal to 1, immaterial of what it is. Always omega equal to 1 for this term S. Draw a line of plus 1 slope if this is the numerator. A 0.1 means you go to 1 and you go to 10, go jump by 20 dB. But this line is extending towards right side and left side also. Remember previously it was only along the x-axis up to 0 here. So this was something like a step. But here it is simply a straight line from minus to plus. Okay. So this is as omega increases, the magnitude is increasing. So the term is in the numerator. If the term was a denominator term, S, 1 by S, as omega increases, its magnitude is going to decrease. So this will be opposite of this one, mirror image of what you have drawn over here. So it is at 1, it is 0 dB. At 0.1, it is 20 dB. Here at 0.1, it is minus 20 dB. But as omega is increasing, the decibel level is more and more negative. That's one. And what is the angle? This S equal to j omega, the angle is always 90 degrees, immaterial of the omega. Therefore, we have a straight line of 90 degrees. This extended beyond the y-axis shows that this has come from a S or 1 by S term. That's all it shows. Otherwise, I could have drawn from here itself, from the y-axis. But slightly showing it projection outside tells you that this fellow has come from minus infinity. Okay. So for a numerator term, it is plus 90 degrees. For a denominator term, it is minus 90 degrees, right, for all the omega. I'm not going to details of this quadratic term. You have to go to a textbook, and that is a lot to tell about. But I'll tell you in brief. There's no difference here. S by omega n, remember that. At omega n, so this is the value of omega n. To the left, I'm talking magnitude. To the left of omega n, the magnitude is 0 decibel. Okay? We are not looking into zeta now, for the time being. To the left of omega n, the magnitude is 0 dB. To the right of omega n, the magnitude is, or the slope is double. That is 20 dB per decade was the slope for a first order term. This will be 40 dB per decade. That means if this omega n go to 10 omega n, the jump is 40 decibels. repeating. This is omega naught, and this is omega naught, and I go to 10 times omega naught, and the jump here is 40 decibels. So this slope is going to be not 20 dB per decade, but it is 40 dB per decade. And the dotted line again are based on various zeta values. For zeta less than 1, the plot will be in the downside. Zeta more than 1, the plot will be on the upper side of this asymptotic straight line. If you go to the plot of magnitude of 1 by s square plus term, the quadratic term, is a mirror image of this up to omega. You to go to omega n, at omega n, to the left of omega n, the decibel is 0. To the right of omega n, go to 10 omega n, go down by 40 dB. Why down? Because it's a denominator term. So logarithm of 1 by magnitude is log 1 minus log m. So minus it comes. So minus decibel. So that comes as a minus 40, not 20 here. Is minus 40 because of the second degree term. And strictly speaking, for zeta less than 1, the plot will be upper side of the straight line. For more than that, it is going to be lower side. This is a mirror image of this. Go again to the phase angle. Omega n or omega naught is the critical corner frequency. 1/10, you go there, that is 0 degrees. 10 times you go, so the angle is 90 degrees for the first order terms. The second order term, so the angle here is 180 degrees. So omega naught, you take a point, go to the left 0.1 omega, to the left of all those points, straight line under 0 degrees. Go to 10 times omega naught. Omega naught is what you have divided, z by omega naught, etc. 10 times that, the angle is 180 degrees. Here's a straight line of 90 degrees per decade because it is double the slope. The dotted line again shows the exact value, again a sigmoidal curve. For a denominator term, again it's the mirror image. Go to omega naught, to the left of omega naught, 0.1 omega, 1/10 of omega naught, angle is 0. To the right of 10 times omega naught, the angle is minus 180, minus 180 because second degree term, so twice 90. So minus 180 degrees, straight line after this one. From 0.1 omega naught to 10 omega naught, a straight line. It slowly increases the phase. Effectively speaking that, the phase angle is more effective for all frequencies between 0.1 omega naught and 10 omega naught. Rest are constant angles. So the transfer function acts as a constant phase beyond this. Suppose there's a term, s by 10 square plus 2 zeta s by 10 plus 1. So 1 omega equal to 100. The phase angles varies linearly. Beyond 100, the phase angle is constant here. That's the case in the first order also, first order term also. Of course, that doesn't apply for s or 1 by s because it's constant angle 90 degrees throughout. Whereas here also, if it is less than, the frequency is less than this omega naught, there is no phase shift. But when the phase shift less than, when the phase angle is to be considered, it is between 0.1 omega and 10 times omega. The phase angle changes as frequency changes. And beyond 10 omega, this is going to be a constant angle. Can you note down the name of an electronic device that is a constant angle beyond the frequency and a variable angle proportional to the frequency between in the frequency band? So you should be able to know this, that its transfer function will be same as this one. Okay, that is an exercise for you. Okay, Now I am bringing back that transfer function plot which I gave in the first. I am now taking this as a 5 into 10 power of 4s to make it simple. I would have made a second degree terms also, but that will unnecessarily complicate things. So the simple one, 5 into 10 power of 4s divided by s plus 5 into s plus 500. This is a transfer function given to you. So to bring to the common form, you take away this 5 outside, 500 outside, and simplify it, it becomes 20s by 1 plus s by 5 into 1 plus s by 500. So if I want to plot this 20, you can see this line with a pink line. I think you can see that. I have no way of can I increase the. Okay, I think I should be able to. Can see the 20 equal 20 dB. 20 I have marked here. That k value 20 is marked here. That's equal to 26 decibels. So this is 0 decibel, 20 decibel, 40 decibels, 60, 20 decibels jump. So this is 26 decibels, a straight line. So this represents K, not the black one, this pink one, whatever color you call. And 1 by S plus 5, corner frequency is 5, so it is 5. This is 1, this is 2, this is 3, this is 4, and this is 5. So the thickness of my straight line is bigger than the width of the bands, doesn't matter. So up to 5, corner frequency is 5. So mark the corner frequency by a line here. So you can draw a line as a corner frequency. And you can have a line here as a corner frequency. Another line as a corner frequency like that. We can have, my line is thicker than whatever it is. Let me try a smaller, thinner one. So you can mark this as a 5 and this as 500. Okay, and to the left of this 5, the decibel is 0. So this whatever called this is 0, and beyond 5, it is jumping by 20. It is a denominator term, 20 dB downside. So if you say the similar point here, this is a similar point here. So this jump is 20. So this jump, I will try to mark it if we can succeed in that. This jump is 20 decibels, sorry, it is inclined. This 20 decibels downside. So this straight line that shows minus 1 slope. Similarly, the term 1 plus s by 500, up to 500, for all frequency, it is going to be, for all frequencies left there, 500, it is going to be 0 dB. And beyond 500, it is a slope of 1. You can say this jump is, again, jump down is 20 dB because it's a denominator term. Now, one more term is yes here, that passes through 1. This is the point 1, where this minus 20 dB to plus 20 dB, 40, 60, like that goes a straight line of slope plus 1. So we have got 4 lines. One is this pink line, green line, the blue line, and the reddish line, whatever you call it. I had to add all these things, this summing up. Adding means it's just whenever a corner frequency comes, what is the magnitude add? That's all a simple way. So just first a corner frequency here. So we add this, okay, this much to this. This is added over here, and the value of k is this much, plus the value of s is this much. Adding these two comes to this point. Come to this point. Sorry. Now at this corner frequency, similarly, you have a negative decibel, a positive decibel, and later on it comes. Look at this. The slope on the right hand side of this 500 is, there are 2 minus 1 slopes. One is green, other is the red one. 2 minus 1 slope and 1 plus 1 slope. Plus 1 is because of the S term. That means beyond this point, the slope of the final line should be only minus 1, because minus 2 slopes, minus 1, minus 1. 2 minus 1 makes minus 2 slope, and this S term brings plus 1 slope. The net slope will be equal to minus 1. So after this critical point, this kind of frequency, this will be minus 1 slope. So this black line is overall Bode sketch of the magnitude of this transfer function. Same way we take the phase angle. I need not tell that is 0 for the, so I have plotted for 0, and this yellow is for this one, but 1 by s plus 5, this is a slope of minus 90, and this green goes minus 90 here afterwards, and this is s goes 90. Adding all these things at corner time. Only corner places you add, rest you join by a straight line. So this becomes your final phase angle. So this is a phase lag circuit, because as omega increases, the net phase angle is going to be lagging. So this is phase lag transfer function. Okay. And the other type of plot is called a polar plot. This is the basis on which we develop our arguments for the stability. So in the polar plot, a radius vector r and the angle of the radius vector theta. These are the two parameters against which you have a polar plot. So the radius vector is taken place by the amplitude of the transfer function, and theta, the angle, is taken by the phase angle of this. So if you sketch, that means at one frequency, it will be A1, phi 1. So R will be A1, theta will be phi 1. Another frequency, omega 2, the amplitude will be A2, and angle is phi 2. So another point, R is A2, theta is phi 2. Go on continuously joining them, that brings you the beautiful polar plots. Nowadays, you have got standard software, MATLAB, a lot of things are available. Okay. A polar coordinate set r theta as A and phi. Remember, again and again, I stress this point, phi is always in degrees. We obtain, of course, there is a lot of confusion. J omega is in radian always. So you have to convert that whenever you plot into degrees. The major mistake I have seen in the control system papers, when the answer is, they will simply add j omega plus this angle, not converting both into degrees. Okay. Let us try to get a phase plot of a polar plot of a first order system. It's very elementary, but I want to stress some points over here. So k by 1 plus tau s, this is what exactly we have seen last day in the first order system. You can convert s into, trace s into j omega as shown over here, but let us try without that also later. So when omega is 0, that is as well as s equals 0, the magnitude is k, and there is no angle here, so it is k. If you plot, if you have a plot over here, look at this. This is a plot, a real part, imaginary part, though I say, but it's a polar plot. Remember, though I have marked real and imaginary, is really going to be a radius vector from this point to this. This one radius vector I have shown here. So the angle is 0 and the magnitude is 1. Fine. At omega is equal to 1 by tau, let us take some value, intermediary values. If you say the 1 by tau, if you remember that, it is a value at the decibel level 1. Let's see that one. Omega equal to 1. This tan inverse, the angle becomes 1 by, the omega is 1 by tau. If you take the omega is 1 by tau, tan inverse 1 becomes 45, the minus sign, minus 45 degrees. So a radius vector of minus 45 degrees. And this is going to be 1. So okay, by root 2. So that will be the magnitude over the function. And you have a sketch over here. Okay. So these are the points which you get for various omega. You get a plot like this. That is just a beginning of a plot. When omega is pretty large, omega goes to infinity, this 1 plus tau s or 1 plus tau j omega will be just j omega only, j to omega only. K by omega becomes 0 as omega goes to infinity. So it is 0. And this, when this is going to be infinity, this angle is going to be minus 90. Remember, we have to justify whether it is minus 90 or minus 91. There are some places I will tell you later on. Is it minus 90 or minus 91 or it's minus 89? I mean, what I mean is, it is a 90 minus or 90 plus. Just above 90, just below 90. Or just above minus 90 or just below minus 90. We have to do that justification later on when you want to analyze certain plots. We will see that shortly. Okay. Now the plot of any transfer function one minute, I will go to this 125. It's good enough. I think all of you can see this 150 will be better. That's good. And sorry, here is a plot, a phase angle and magnitude in the Bode sketch. This I introduce you to the most prominent specification in frequency domain. These are the two specifications which are quite prominently used in the steady state. See what happens, a system should act in a specific way in a transient state. So what we saw yesterday, the transient behavior and the MP, TP, TS, etc. I will guide that one. And the frequency response type, that is steady state behavior, is controlled by or is expressed, the desire of that is expressed in terms of these two terminologies, gain margin and the phase margin. They are the most vital specification in the frequency domain, whereas we have got MP, TP, TS, TR, etc. in the transient stages. So you may not be happily satisfying both the ends. Something you have to give it. So this is a decibel, is a Bode plot of a thing where the Bode plot is crossing 0 dB line. That is called gain is crossing. The gain is crossing from positive value to negative value. The other also is true, from negative to positive also, this way also you can, that's also gain crossover. The first time then the gain is becoming 0. 0 dB, not to 0 magnitude, 0 dB. 0 dB is nothing but gain equal to 1. That gain equal to 1 is an important point in your stability. We will see that. So gain equal to 1, that is called gain crossover. Similarly, when phase angle is 180 degrees, plus minus. If it is minus 180, add 360, make it plus 180. So that is called a phase crossover. So you have got a phase crossover frequency and a gain crossover frequency. The frequency at which the gain is equal to 0 dB and the frequency at which the phase angle is 180 degrees. Recently, I saw somebody ask me a question. If gain, okay, we will come to that question. And look at this. You take the gain line and correspondingly look into the phase line. From the gain crossover, connect with the phase angle. So the angle by which, if you add that angle, the phase angle becomes 180. See, this much angle I can add to the phase, this is a phase margin, phase plot. This much I can add to the phase angle at the gain crossover, so that this point becomes at 180 degrees, 180 or plus minus 180, doesn't matter. So that angle addition is called phase margin. Go to the phase crossover, correspondingly go to the gain. How much can I increase the gain here? Of course, remember, the gain here is in negative dB. That's why I'm calling increasing. Or multiply in the number field. So we are talking about in logarithmic scales, the zero. So the decibel, this may be minus 10 decibels, this point, corresponding to the phase crossover. How much I can increase? Suppose it is minus 11 dB. I can increase the gain by 11 dB so that this blue line will cut here. This becomes the gain crossover. So if gain crossover and phase crossover coincide, system has a 0 dB gain. That's all. Somebody was asking that in one of the what you call Quora or whatever it is. Okay. Let us look into the same plot, slightly shifted right side or left side. Here is your gain line, phase line. Okay. This is your gain crossover, and this is the phase margin. So I can this angle is something like minus 150. So I can add minus 50 more. That means a positive phase margin is there. If you go to this place, and what is a phase crossover? This point corresponding to the positive, I can shift up. That means I can increase the gain so that this point coincides with this 0 dB line. Come to this kind of a plot. Here what happens, see here, look at this, the gain crossover is appearing first and phase crossover appears next. So phase crossover follows gain crossover. Here it is the other way. Phase crossover has already appeared, then comes a gain crossover. So that's the opposite of what we have seen last. Yes. Now, so here the phase the phase angle is 180 here. The gain is already more than 1. So if you want to make it 1, I must reduce the gain. So the gain has to be pulled it down in decimal. Pulled down means in the decibel level. Here it is, the gain has to be pulled up so that to make gain equal to 0 dB. Here you have to pull it down. So these are the two different aspects of gain crossover and phase crossover following one of the other one. Phase angle, what happens here? Here phase angle is something like minus 140, 150. Let us see what happens here. Here the phase angle will be, the phase angle here is plus something like plus 20, plus 30 like that. Minus 270 means in the second quadrant. So I have to push up the phase angle so as to make that as the phase crossover. So these are we will come to this Y phase shift, etc. when you study the stability. Now there is I got only about 45 minutes. Let me see how much I can take you to. Of course, I will go a little faster here. You take an S-plane where a real part is here and imaginary part is here. Let me see whether I got that or not. Okay, I'll do that later. Okay. This should be closely followed because there's some convention. People get confused with this convention. Even I've seen some class notes and some teachers taking this stability, put in the opposite of what is real because of the confusion between the clockwise and anti-clockwise. I wish everyone follows strictly one method and accordingly. See, something like voltage drop, is it positive or negative? When you have a circuit problem, voltage drop, is it positive? Is it negative? You take your passbook, for example. In your passbook, you have withdrawn 100 rupees. So that will be shown in the bank account. They have lost 100 rupees because they have given away 100 rupees to you. But in your account, the very same 100 rupees is a gain. So in one side it is a loss, or that is a debit. Here is a credit for. In your account, that will be CR. In their account, it will be DR. The same 100 rupees. But the operations are different. From the counter, it goes out, and into you, it comes into your counter, your pocket. So it's a convention again. That about the 100 rupees, let us see. You have a closed contour, closed path. You trace, see, for every point here, you have got, I'll show you. For every point here, there is some value of S, real or positive or negative. For example, if you have got a point here, this point I am referring to, minus plus J. So minus 0.5 plus J3, something like that. So this may be plus 3, okay, plus J1. This may be plus 2 minus J1, something like that. So these points, every point has a value, S value. So this is a closed contour, we say. The contour is a trace, is a travel path. Okay. For every value of S here, you compute some function of S. This function of S is important function of S for us. This is the bread and butter for our life. This Fs is nothing but Gs into Hs. Later on, we will come to that. Let us call f of S, some function of S. For every point here, S1, S2, S3, S4, S5, find out what is Fs1, Fs2, Fs3, okay, and plot them. So if we plot and continue the same order, 1, 2, 3, 4, 5, 6, 7, 8, 9, here also F1, F2, F3, F4, F5, continuously join them. If this is a closed path, this is the first rule. This Fs will also be a closed path. If it is open, like say U, something like that, or a parabola, this also will be open. If gamma is a path which we call in the S domain, just for a naming sake, this Fs is a map we call. Just for us to understand in this lecture of dark room, because you don't see me, I don't see you. So gamma is the sketch of a closed loop in S domain. So this is S domain. In Fs, this is also real part, imaginary part. This is a polar plot also. All are same. Fs is continuous. Now look at this. For a closed contour gamma in the complex S plane, the locus of F we call mapper is also closed. If gamma is in the S plane encloses, now what happens? You choose about the poles and zeros. Attend very carefully here. This is a place where we normally topple down in the analysis. If the number of poles, the first, as I said, maybe it will be a rational polynomial, a numerator polynomial and a denominator polynomial, rational polynomial. So numerator equal to 0 gives you zeros, denominator equal to 0 gives poles. I'm not concerned about all the zeros or all the poles. I want to take those number only, not even the values. The number of poles and zeros of f of s, which are inside this contour. There may be a pole some outside here. There may be a pole outside. Okay. You might have a pole somewhere here. You might have a pole somewhere here. You might have a zero somewhere here, somewhere here. I don't bother about those things. Only those poles and zeros that lie inside this contour, which you have chosen. Please make it a point again and again. It's worth repeating it. It is only those which of Fs, poles and zeros, which are just inside this contour only. Not all the poles, not all the zeros. We don't bother about them. We don't bother about their values also. Number only we want. How many poles of f of s and how many zeros of f of s are inside this? For this picture, cross is a pole, circle is 0. So there are 3 poles and 1 0. Okay. So 3 poles and 1 0. Okay. That you keep in mind. Now go to f of s. As I said, if this is gamma is closed, fs is also closed. The map. Draw a radius vector just like that, a radius vector like this. Okay. How does this encircle this center point? This is, as I said, S1 to S2 to S3. That means if this is S1, S2, S3, X4 clockwise, you must also make it as S1, S2, S3. And it may be clockwise or anti-clockwise. Doesn't matter here. In this example, it is anti-clockwise. But I am making this as clockwise. This gamma is clockwise. That is standard. No change in that one. Fs may become obedient son or a disobedient son. So it may obediently follow the same clockwise or it may be anti-clockwise. So they need not be following the father. Anyway, FFS is in this example. So how many times this is crossing this line? Once here and second times here. I think you can see that. Once over here and second times over here. Once here it crosses and second is here it is crossing. So it is in the anti-clockwise direction it is crossing. Okay. How many times? 2 times. The theorem says the number of times this n it crosses, it encircles this is origin 0 is number of zeros inside of gamma minus number of poles inside. Number of poles is 3, number of zeros is 1. So n must be 1 minus 3. It should be minus 2. What is the minus 2 telling? If this is clockwise, this will encircle 2 times in the other direction, anti-clockwise. If gamma is clockwise, if you get minus 2 here, it is going to be anti-clockwise. Another example is, I have chosen a gamma, another FFS I have taken here. Here I have got 4 zeros inside, 4 zeros of Fs. Fs might have 20 zeros and 70 poles. I don't bother. How many zeros are inside this one? 4. 2 poles. And the number of encirclement of Fs will be n. It is 4 minus 2. That is going to be plus 2. That means it's a faithful son following the same way as a father. This clockwise is also clockwise. You see this radial vector? It cuts here clockwise 2 times. So n equal to 2. Why do you want this? Suppose you know P. Suppose you know P. Okay? And you know N. Okay? So you can compute how many Z are inside. That is the crux of the problem. How many Z are inside? That is the one that decides stability. Exact shape of gamma or Fs is not a matter. Okay? Again, stress these 2 points. Pz and Zz are not all the poles or all the zeros, but they are those numbers which lie inside the gamma. Only number of poles and number of zeros. Let us take an example here. So we are using this theorem. This is a Cauchy's mapping theorem or principle of argument. Argument is the argument of the angle. So A angle theta, the theta is called argument. This is the principle of argument, or it is not an argument in a court. It is argument is the angle theta here. Cauchy's mapping theorem. This is a vital theorem based on which we can predict the stability. So let us prepare that. It will faster it will go. So stability criteria. So closed loop, say, the closed loop transfer function is g by 1 plus gh. So this 1 plus gh is called the characteristic equation. The roots of this characteristic equation is the pole of the overall transfer function. So if the transfer function, overall transfer function, and its response should be stable. It should not go to infinity. So all the roots must have a negative real part. These are the basic things in a stability. If it is not, what happens when you take the transfer function? You will have terms like 1 by s minus 1, 1 by s minus 3 like that. So the corresponding response will have e power of plus t, e power of plus 3t, which will never die. As time goes on, it becomes unbounded. So any pole on the right-hand side or the positive real part will always bring the system to instability. So we want to see whether there is any pole on the right. We don't want to know exact location. We want to see, do we have a number of poles of the closed loop on the right-hand side? Yes. Say it's unstable. No, it is stable. Like that, we want to have a digital question and digital answering. Let us see that. How to do. On the system poles, and see, just this may take a minute or two. It may lead to certain confusion to students. So 1 plus GHS is the is a loop transfer function. See, forward is G, feedback is H. So GH is a loop transfer function. That is the form of some polynomial PS by some polynomial QS, rational polynomial. What is 1 plus GH? So 1 plus GH is 1 plus P by Q. So P plus Q by Q. Look at this. These Q zeros of the roots of QS are the poles of GHS. Okay? And the poles of 1 plus GHS are the same as Q. So the poles of 1 plus GHS are the same as the poles of the loop. Zeros of 1 plus GHS, that is what we want to see. Why? Because 1 plus GHS comes in the downside, that becomes the pole of this overall system. So 1 plus GHS equals 0, its roots are real poles of the closed loop system. Here 1 plus GHS will become 0 when P plus Q becomes 0. That means the numerator of that becomes 0. That means the zeros of 1 plus GHS. That's why it is zeros of 1 plus GHS. So system characteristic equation, its roots are called overall poles. They are same as zeros of the poles of the system. Okay? Poles or the system, not the 1 plus GHS, is same as the root zeros of 1 plus GHS. Now, if I plot this GHS, okay, and see the encirclement, if ZR, now I am putting the word R here because just to show that it's a right side, PR. The number of zeros of 1 plus GHS, zeros of 1 plus GHS, which lie on only on the right of plane. PR, the number of poles of 1 plus GH. Poles of 1 plus GHS is same as poles of GH. So their GH is called open loop. So this PR is nothing but same as open loop poles. Okay. So when you know the loop transfer function GH, I know how many poles are there on the right hand side. How many? Not all the poles. For example, if GHS is 1 by S into S minus 1, there is one root on the right hand side. S minus 1 gives you S equal to 1 on the right hand side. So PR equal to 1. We do not refer to the total number of zeros. Let's come to this point here. Procedure to apply is a blind man's walk. So you are given, I said Fs I'm going to rewrite later on by Gs into Hs. Given the open loop transfer function, choose a contour gamma to exclude the poles at the origin or along the j omega axis. If there are some poles only along the j omega axis, avoid them. How to avoid, we will come to know just now. See that. It is something like a man walking along the j omega axis, coming a big circle on the right hand side and walking along minus j omega and coming back. It is something like that. You have a semicircular path. One vertical side is something like looking like a D. Vertical side is j omega and minus j omega. And the right hand side is a half circle. You walk around that, 0 to infinity, then around the semicircle, and then back to the negative axis and go back to origin. So that's it. And if there is somebody sitting on your path, what will you do? You will avoid him, you will go around him. If somebody is sitting on your way, he sits, people are there who will sit on the way. So what you do, you avoid him, you make a small circle around him. I have all given instruction that you must go only on the right hand side. So you must avoid that fellow, give a small circle around him to avoid that fellow. That fellow is a pole on the j omega or at the origin. Okay. So sketch the polar plot using these values. That you have to compute the value of gj omega, hj omega at omega 0 and omega infinity, and plot the polar plot. Let us see how your polar plot is going to be. Before that, the counting the encirclement. So after plotting that, the number of encirclement about the origin is GHS origin is actual origin. 1 plus GHS for the same plot is -1 is the origin, because I'm shifting it to -1. The origin is shifted to -1. So the any length will become HS become 1 GHS become 1 plus GHS. So the origin is 0, 0 for GHS. For the same plot, -1, 0 becomes the origin for 1 plus GHS. That is a simple geometry point. An analytical geometry point. Sometimes you use the word -1 J0 or just say -1 0. That makes not much of a difference. N is positive, the encirclement is in the same sense as gamma. Otherwise, it is negative. For our class, that gamma be always clockwise. I go around that path always clockwise. Let us see that. Using the relation n equals ZR minus PR, obtain ZR equal to n plus PR. PR is the poles of the GHS, the open loop function. This is already known a priori. So we know this a priori. We know n by seeing the picture. So we compute ZR. The Nyquist stability criteria says that the number of encirclements of G omega, H omega about the critical point. Critical point is at -1, 0, be n. If the open loop is unstable, that PR is not equal to 0, so ZR equal to n plus PR. Okay. Stable open loop, PR is 0, ZR equal to n. What is your interest? You want to know, is there any ZR? If there is any ZR, that means 1 plus GHS equals 0 has one root on the right-hand side. System is unstable. So to be stable, whatever be the condition, ZR should be 0. So if ZR equals 0, the closed loop is stable. If ZR is not 0, it is not stable. So we have to compute ZR. So the whole step is draw, count n, a priori knowledge of PR, compute ZR. ZR is 0, then say it is stable. If ZR is not 0, say it is unstable. Let us take an example of this. So we have got 3-4 problems. We'll try to solve this. Sorry. So we are always given open loop transfer function. We are not going to calculate anything of closed loop. No closed loop transfer function is going to be computed. Open loop transfer function only is the loop transfer function, sometimes they call, or open loop transfer function. GHS only is going to be used throughout this. There is no, you can make it a note here, there. You should not compute 1 plus GHS in any of these problems. Some problem may be asking you that question. In computing the stability, no need to look into 1 plus GH. We have only the loop transfer function GHS. So, is GHS. K is a variable, a number you can vary. So, we plot the whole thing with K equal to 1 because we don't know what K is, though I may use K here. So, F1 of J omega is here. Put S equal to J omega. I think these simplifications are easy for you. You can do is J omega, 3 plus J omega, 6 plus J omega, etc. And there is no pole of this f of s on the right-hand side. The poles are at -3 and -6, but there is no pole, no term like the denominator s minus 1. No, I don't have. So there is no pole on the right-hand side. So PR equal to 0. This is by looking at this. Nobody need help you. Look at this transfer function, say PR equal to how many? No, 0. Now for S, see J omega 0 means S is 0. J omega. When S is 0 is same as omega is 0. So when S is 0 or omega is 0, is K by 18 is a value. And so k by 18, there's no angle here. You can see that omega is 0 in this expression, k by 18 minus 0 plus j 0, which means it's a real number k by 18. So you mark a k by 18 some point here on the real axis. So this corresponds to omega 0. This length corresponds to k by 18. Okay. I'll try to change this one. It's convenient for me. I can draw, so I want to write also. So you have marked here. PR equals 0 is already known. K by 18 you are marking. Omega is infinity. Omega is very, very large. So it becomes k by s square. Okay. That is k by minus omega square. This s is j omega in a j. So it is going to be 1j minus j into minus j, because this s is j omega, k by j omega into j omega. So this j becomes minus j here. This becomes minus another one more minus j. This minus j is a minus 90. This angle is minus 90. So the angle is minus 180. That is same as plus 180. So the angle is 0, angle 180. And just look at this. It should be very carefully looked into. Will it cross 180 is this line. See, 180, for example, 180 is this line. This line is 180. Will this plot cross? Just you see that this angle can be maximum 90. This angle can be maximum s plus 3 can become max. This s plus 3. The maximum angle is 90. So it can be at the most 89.999 when s is really very large. S plus 5 is also maximum 90. It can never cross 90. Then s plus 5 is when s is infinity. Infinity is not a number. So very large number. It is going to be again 89.99, something like that. So this will be 179.999 only. So it will never cross this real axis. So the plot will be starting at this point, okay, ending at this point like this. So ending at this viewer. And somewhere intermediary point, you can say that at this point, the value for the radius vector, the value of real is 0. When the real is going to be 0, when is the real going to be 0? This is going to be 0. So omega is equal to root of 18. When omega equal to root of 18, you compute the value of this loop transfer function. That becomes minus k by 9 in the root of 18. So that is the minus becomes this minus downside. So this is what it is going to be, the value, of course, k. So you have now this point, you have this point. We don't want any other thing. So we have, really speaking, we have 3 points. One is here, and one is here. So I can say this is going to be the plot. I can say that. No, it's going to be outside here. And here is your minus 10 point. This is a critical point. And is for omega is positive. That is for all the values of omega here and omega here, the black one is a plot. So for all other values of omega here and omega here, the corresponding plot will be mirror image of whatever you have drawn over here will be. So the mirror image of this will be the plot for negative omega, is for the positive omega. Now this is a complete FS map. So this is my F map. My minus 1, 0 is here. This is minus 1, 0. This is not inside this, no. So the number of encirclement is equal to 0. So we have here the encirclement is going to be 0. PR is 0. So ZR equal to n plus PR, 0 plus 0 equals 0. There are no roots of 1 plus GH. So no roots of 1 plus GH of S, no roots on the right hand side. So it is stable. So that is all the things that it talks about the stability of Nyquist rate. Let us take 2 more examples. Okay. The next one is slightly involved. Doesn't matter. We'll see how best we can solve this problem. The loop function is k by s into s plus 2. The difference between this and the previous is there was all the poles were on the left side, s plus 2 and s plus 3. If you see the previous one, it is s plus 3 and s plus 6. They are all on the left hand side. But here, one is okay left hand side, the other one is at the origin. So there is a pole at the origin. So we are tracing the path of all s along this semicircular set. But there is somebody sitting here. There is someone sitting there. Here is a pole sitting. I don't want him to go inside my contour. So what I do is, I will make the contour just go around him this way. Go around him this way. So my contour is clockwise again. So I am going clockwise this way, okay? My contour is clockwise. Now, for all points along this omega 0, the C is very close. Remember, C is not some value. C is very close to this point. It may be 0 plus. 0, C equal to 0 plus. That's all. Very, very little. Or you can say epsilon, you can call another way. You can write. When it's omega 0, the value is k. Let us see. When omega 0, what happens to the value? The value here is, I've shown here. Omega 0 means this is going to be 0. So k by 0 is going to be infinity. This infinity doesn't speak anything. It's a very, very nice for Ramanujam and the mathematicians. But for us, we don't like the word infinity. We want to have concrete value. So infinity is what? How does it come? So to find out, you should, strictly speaking, split this into real and imaginary part. Yeah, I have done it over here. So this is going to be k into minus 1 plus j2 by omega square plus 0. When it is infinity, okay, this omega is starting point. Let us start. Omega 0, look at please. This is going to be, this is going to be 0. So minus j2 by 0, that becomes minus j infinity. And this is going to be 0, so this is minus k by 4. So what you have got is when omega 0, you have got here minus k by 4 and minus j infinity. This is what you get here. Now we have a point here, minus k by 4 minus infinity. So I go somewhere here. So this is the point that corresponds to this minus k by 4 and infinity. So this is starting point. Okay. And when it is very, very large, what you have is the value here is 1 by s gives you 90 degrees, minus 90 degrees, and 1 by s plus 2 when it is very, very large. This also gives, look at this 1 by s plus 2, this term, this 1 by s plus 2, when s is very, very large, gives you the angle, I'm talking the angle only, is very, very nearly, how much? Minus 90 minus, that means something less than 90, because s is going to be some number. So tan inverse 10,000 divided by 2, that is tan inverse. So it's going to be minus 89.999. That's important number. It's not 89.9, it's very, very close to 90. So minus 90 due to the 1 by s term, this is j omega. So 1 by j omega, that is 1 by j becomes minus 90 degrees and minus 89. So it is something just less than 180. It is not above 180. So we have a point here in this plot, a vector in here. It is not this way, but it is this way. So this angle is minus 179.999. It is just, this number is just to make you understand that it's less than 180. In fact, that when you take, it will be 180 only. But it's starting at the C point, the C here. So starting at this point and ending at a point somewhere here. So this will be the plot for all the values of omega on the positive side. On the negative side, a mirror image will reflect. So you can have it. So this is the minus omega, this is plus omega. And when for a small circle, that is this small circle, when it's tracing the small circle, the S value is 0. S value is 0 means the magnitude will be very, very large. Here it is anti-clockwise, this is the clockwise, opposite direction. So we will have a plot which is this way. Sorry. It is not there. So this is the starting point. It goes this way because this is omega equals 0 point here. So it goes this way, it goes this way, it goes this way. Remember, here is your minus 1 point. So it is not enclosing minus 1. So n equal to 0 and there is no PR and this gives you ZR is 0, system is stable. Okay. To check whether the system is stable for all values of k, you may compute 1 plus GH and find its roots. That is another problem. Here is another, shall I go a little fast? Here is another problem, which is one pole on the right-hand side. One pole on the right-hand side. So here also I plot, there's a pole at the origin. So I had to avoid that through a small circle and take all the values of omega 0. When omega 0, the value is infinity. But look at this. The value of infinity means this is how, in fact, this is the real part, this is the imaginary part. So when omega is equal to 0, this minus k by 1 plus j, k by 0, that is plus j 0. So the plot starts at minus k by 1 and so somewhere here. So this is the starting. I think my name is coming over here. Sorry. Okay. Okay. So the starting point is here. And since, look at this. Is it time? No. Starting point is here. And I have given this. Omega is very, very large. It is 0, 180. So it is going to be the point. The point is going to be somewhere here. So it starts at this point, comes this way. So this is the way it traces for positive omega. So for negative omega, it will trace the S6. It has come up to here. Now this FABC I have given here. This is the way you must try. FABC, this small circle of infinitesimally small radius R. So any point on this FABC, so if I plot that FABC, this is FABC in a bigger scale. This F and this A is somewhere in between. I just put for us to understand. So this angle is 45. I kept it here. So a point F or A or B or C can be designated by R theta, where theta varies from minus 90. So this is the R theta minus 90 to plus 90. And R is tending towards 0. When R tends to be 0, the value is going to be infinity. But I want to know how the angle changes. So when you substitute this R, A, J theta in this, you can arrive at this, sorry. I'm very sorry, this comes out of, okay. Look at this, when R is going to be infinitesimally small number, so 1 by R becomes infinity. So the angle is important here. Why? Because the way in which by which it is rotating. Now let us say the F map has this angle, minus theta. This is my interest. And what is the gamma map FABC? F point is minus 90 point. I'm talking that infinitely small radius. The angle only we take. A corresponds to 0 angle. B corresponds to, let us say, 45 degrees. Okay. C corresponds to plus 90 degrees. So this is what it is now. So substitute here for the angle minus theta plus 180. You get the angle of the corresponding mapping points as 270, 180, 135, and 90. So starting at F, if we say, okay, I don't know where I am. I'm here. Okay, this is the place. This is the place you start with. So you have got 270. Then you have got 180. That I have marked here. This capital F corresponds to small f. Capital A corresponds to small a here. I have marked here. So that comes as 180. The B corresponds to 135 degrees. So this is 135 because this is 90, this is 45. So this is 135, this is 180, this is 270, like that. So this is the way the map goes. The map goes this way. Now, what is this point? This is at infinity because the value is infinity. So your power minus 1 will have to be somewhere here only because this length is infinity means minus 1 is here. So there is an encirclement in the clockwise sense. The clockwise sense, this is the way it goes. So n is in the clockwise sense, n is equal to 1. So we have n equal to 1 here. N equal to 1 here, and ZR is 1 plus PR. PR is always 1, therefore n equal to 2. As n equal to 1, ZR equal to 2. N equal to 1, PR equal to 1. So the ZR should be equal to 2. There are 2 closed loop poles, therefore system is definitely unstable, whatever be the value of K. Okay. Now, I'll skip this one, if you can understand easily the same way. I prefer your drawing should be based on the angles rather than the actual computation of values, because angles will tell you how it goes. Here is a typical problem. Of course, I'm skipping this. If you want, I can tell you. This is a third order. Again, start one by starting at minus infinity, and you can compute it with the real and imaginary part. So this point you get, and the maximum angle which you can get is 90. This something less than 90. This something less than 90. So this is something less than 180. So something just less than 270. So this is the point where you can at the most get. So this is actual 90 and 270, something less than 270. So 270 is this one. So it will be something over here. And so this is your plot. Now this point you can find when the angle of Fs is 180 degrees. Tan this is going to be minus 90 into this one. Tan inverse omega by 2 minus tan inverse omega by 3. That is tan inverse 5 omega by, you can simplify it. Tan inverse omega by 2 plus tan inverse omega by 3, tan inverse of omega by 2 plus omega by 3 by 1 minus omega square by 6. So that we can see this one. And this becomes infinity. That is minus 90 plus minus 90 is minus 180. So any point here will have an angle of minus 180. Because this is minus 90, this is minus 180. The easy way of finding where it is crossing the real axis. So if you solve for this, omega is equal to root 6, substitute here omega equal to root 6, get the value that is equal to K by 30. Okay. And you can complete this as I said. So if the minus 1 is here, it is enclosing n is 2. If minus 1 is here, n equal to 0. So if minus 1 point is here, if k is let us say k is 10, then this length is 1 by 3. If k is 40, then this is 1.3 something. So 1 minus 1 is here. If minus 1 is here, here is one clockwise, here is another clockwise, n equal to 2. So n equal to 2 over here. So ZR equal to 2. Since PR equal to 0, ZR is 2, system is unstable. So if k is more than 30, the minus 1 point is somewhere inside. If it is going to be here, k must be, k must be less than 0 to 30. If k is less than 30, this point, this length is less than, so suppose k is 20. 20 by 30 is less than 1. So the minus 1 is somewhere here. Therefore, system is stable, no encirclement. So there are two aspects when k is, this is called relative stability. Okay, we call it relative stability. I have another problem here. This was a gate problem recently, not about a year back asked. You are given a plot. We are not bothered about this. An example I'm giving you. But it tells you that the PR is 0. There is no pole on the right-hand side. So PR is 0. He has given points like k by a, k by a, k by b, etc. he has given. System stability. The minus 1 point is here, 1. So minus 1 point can be anywhere. Minus 1 point is here, minus 1 point is here, or minus 1 point is here. If minus 1 point is here, is a clockwise and a clockwise, so there are two encirclement, so n equal to 2. So if n equal to 2, PR equal to 0, ZR equal to 2, therefore system is unstable. If minus 1 point is here, when will be a minus 1 here? K by a is more than 1. So k is more than a. So this length will be more than 1. So minus 1 will be here. If k by a is less than 1 and k by b, this k by b is more than 1, the minus 1 can be here. But here the encirclement is one anti-clockwise and another clockwise. If you take a radius vector here, one is going anti-clockwise, other is going clockwise. So n equals 0. So n equals 0 here means ZR equal, because PR is always 0. ZR is 0, so system is stable. That means system will be stable if it is k by a is less than 1 and k by b is also less than 1. Here, k by b is more than 1. K by z is also more than 1. Then minus 1 will be somewhere here. So here also n equal to 2. From here, if you draw a radius vector, this is a clockwise, this is also clockwise. So n equal to 2 here, and that makes the system unstable. So I have given two stable region, two unstable region and one stable region based upon the relative values of A with K. So the last two problems tell is the relative stability or the conditional stability. It will be stable if K is less than 1, less than 2, less than A, like that. That's all the basics of applying Nyquist stability criteria. There are many more things in that. I don't think I have covered everything under the sky. But this will give an impetus to work more on the problems. If you have any difficulties, any problem, you can email me any time of your own convenience, either individually or as a group. I will try to answer them as much as possible, as much I can. I should thank Vijnan Institute for giving me a good chance to talk to people in a closed chamber. Without seeing mutually each other, we have been spending about 3 hours yesterday and today on a topic of interest generally for the teachers. And my idea was to put forth this in front of the students, because you are all quite well-versed, you are quite capable of understanding these things. For certain points we have to stress when you teach. I will take about half a minute from you. I'll have one question here. We take the frequency response of any transfer function and say that system is unstable. If you say system is unstable, go backwards. How can the polar plot be drawn? How can the polar plot be true? So there is a question here. How can you determine a polar plot when system itself is unstable? but you say system is unstable from the polar part only. So how can the reverse be true? That's one question. Second question is a small working below. Find the impulse response of a transfer function of a system. Take a very basic problem. Transfer function is 1 by s plus 2. So the initial condition is 0. Say 1 by s plus 1. That's a transfer function 1 by s plus 1. And the assumption is that initial condition is 0. Find the impulse response. It will be e power of minus t. Am I agreed on? 1 by s plus 1 e power of minus t. Put t equal to 0. It is never equal to 1. It is never equal to 0, but value is 1. But we started the assumption that initially the system has relaxed, that no output. But now we find that when t is 0, there is an output which is equal to 1. Is it a contradiction of the transfer function? If so, how? If not, how are you justified? Think of these problems, 2 problems. Try to answer me through your email. I should thank once again all the participants and Vignan Institute, Sarath Yadav in particular, and my predecessing professor, and the one who are going to come back afterwards. I thank one and all. Thank you very much. Sharath?
Thank you. Yes, sir. Thank you so much, sir, for your time. It was an informative session, enlightening us in area of control theory. Special thanks for sharing your handout, sir.
Okay, welcome. You can pass it on to them. Let them use that.
Yeah, participants, if you have any doubts, you can post it. Yeah, you can post or you can mail to us. One participant has asked a question, sir.
Yes.
Whether the time-independent behavior of the system is complex in control systems, control design.
Which one?
Whether the time-independent behavior of the system is complex in control design.
Time-independent systems. No.
Yeah, time-independent.
But that they are static systems, you know. See, I want to tell you one thing. When you study the stability of a system, there are 2 stabilities of any system. One is called static stability, other is called dynamic stability. A lot of work is in progress in learned universities in Germany on the dynamic equilibrium of a bicycle. Can you, just a bicycle on 2 wheels, can you make it stand vertically? T equal to 0, because there is not moving at all. Can you make it stand vertically? It is difficult. Okay, central gravity must, etc., all those things. You make it stand vertically with some difficulty, and even a small blow of a wind will make it unstable. This is static stability, time independent, no time in that one. But the very same cycle, you are riding the cycle, you are keeping the cycle inclined or at so many angles, even when the cycle is still moving without falling. So that is a dynamic stability based on time. So there is time independent, that study itself is different. Okay? Hello?
Yes, sir. Thank you so much, sir.
Now, if I didn't clear, again, let him write down. I may.
Yes, sir. Sure, sir. Thank you once again for giving a broad view of control theory, sir.
Welcome. It's welcome time for me.
Yes, sir.
I should thank all of you, first of all, to be patient in this. And for a teacher, I have not seen the faces. So whether he was scratching his head or not, I don't know. I see everybody is following it.
Yes.
Thank you very much.
Yes, sir. Thank you, sir. Thank you so much, sir. For audience, there is a small announcement. Tomorrow's session is postponed to day after tomorrow, and day after tomorrow's session is preponed to tomorrow.
Oh, there's swapping of the 2 sessions.
Yeah, yes, sir. So tomorrow's session will be handled by Dr. I. Tirano Karasu from MIT Manipal. He is taking a topic on energy conservation and optimal use of actuators for pilot plant operations.
Okay.
Yeah.
That's nice.
Thank you so much, sir. That is for the session. We'll meet you tomorrow.